Ghrelin in its mature form is a 28-chain amino acid peptide hormone which not only supports but is crucial in biological functioning. Ghrelin acts upon depleted energy stores and is secreted from gastrointestinal tract enteroendocrine cells, which secrete hormones. Enteroendocrine cells are scattered throughout the GI tract and release several different types of peptide hormones which help to regulate a variety of digestive mechanisms. Ghrelin is secreted from enteroendocrine cells found within the mucosa of the stomach. During fasting, when glycogen and epinephrine levels have risen, ghrelin, which is primarily secreted from the stomach, will travel via the vagus nerve up to the hypothalamus and pituitary. When ghrelin signals reach the hypothalamic arc within the brain, it will prompt for a need in positive energy balance by stimulating appetite and endorsing efficient energy storage. Because ghrelin travels to the brain from the stomach via the vagus nerve, it is recognized as being an effector of anabolism within the brain-gut axis. Ghrelin has been found to be acting within the brain with influence over numerous central and peripheral areas of the body. These include, but may not be limited to, gastric acid secretion and gastric motility, sleep modulation, regulation of glucose metabolism, suppression of brown adipose thermogenesis, anxiety and stress, as well as support in cardiovascular function improvements and protection against muscle wasting. In 1999, a discovery was made that showed ghrelin to be also an endogenous ligand for the growth hormone secretagogue receptor, or GHSR1A. Ghrelin is in fact the third identified capable way of stimulating the release of growth hormone from the anterior pituitary gland. Because growth hormone is anabolic, meaning it requires energy to carry out its function, it is thought that ghrelin assists in coordinating energy needs to support this growth process. Ghrelin is able to stimulate appetite via central and peripheral pathways, as well as through transmitting signals via the vagus nerve. After crossing the blood-brain barrier, ghrelin is then locally synthesized in the hypothalamus. Ghrelin then stimulates MPY and AGRP neuron activity and decreases POMC and CART neuron activity, which in turn increases appetite and food-seeking or fasting mechanisms. Hypothalamic AMP activation protein kinase, AMPK, seeks out energy status of cells and regulates fuel stores by inhibiting ATP-consuming pathways and stimulating ATP-producing pathways to provide reserve fuel from available stores. Once ATP stores have depleted, rising AMP levels induce AMPK activation via phosphorylation of acetyl carboxylase. This results in an increase in fatty acid oxidation. In cells with growth hormone secretagogue receptors, ghrelin induces an intracellular elevation by binding to the G protein-coupled receptor, which activates phospholipase C, or PLC. PLC hydrolyzes some cell membrane phospholipids, which produce inositol triphosphate, or IP3, and disylglycerol, or DAG. IP3 then binds to the IP3 receptor, which is a ligand-gated calcium ion channel within the endoplasmic reticulum, which triggers a calcium ion release. Calcium ions, acting as secondary messengers, cause secretory changes within the cell, which stimulates growth hormone vesicles within the cell to release growth hormones, which then enters systemic circulation via exocytosis. Patients with anorexia nervosa have shown to have elevated levels of circulating ghrelin compared to that of age-matched healthy control subjects. Studies which have implemented dietary interventions with anorexic patients demonstrated with increased BMI scores results in reduced levels of circulating ghrelin. Fluctuations in plasma ghrelin levels are hypothesized to reflect a physiological adaptation in reaction to long-term changes in energy balance.